Hello, welcome to the Linear Algebra Tutor. Here we're going to wrap up our discussion with determinants and all of that stuff we've been talking about by concluding with a few important properties. If you look through any linear algebra book on determinants and get through all this stuff that we've been talking about, you're going to find pages and pages of properties with determinants. There's just lots of stuff that people have figured out about determinants that are useful, nice relations, especially for a math book to tabulate for you. I'm not going to present every relation of a determinant, but I'm going to present the ones that are, I think, important. Some are more important than others, but all of the ones on this list, on these lists, I think are worth bringing up for a good reason. So don't expect to see everything in here. Your book probably has some others, but I'm going to share with you the ones that I think are most important. Okay, so remember when we calculate determinants with cofactor expansion. Cofactor expansion. All right. The first property I'm going to share with you is something that's pretty obvious, but maybe not the first time you think about it. If any row or column of a matrix is all zeros, then the determinant is also equal to 0. If I write it like this, if any row or column is all zeros, then the determinant's equal to 0. You might file it away and say, okay, great. But you may not think much about it, like why? Well, let me show you real quick. Just give you a quick little thing, and then you'll probably remember it. What if you have something like 1, 2, 3, 0, 0, 0, 4, 5, 6. This is our matrix, and we want to find the determinant of this matrix. Let's say, or let's recall, that we can calculate the determinant by expanding about any row or any column. So I can go through this row, through this row, through this row, through this column, this column, this column. And you should get the same answer in all cases. So if we expand about the middle row, what we'll have is this 0 times the cofactor at this location, plus this times the cofactor at that location, plus this times the cofactor of that location. That is the definition of expanding, cofactor expansion, to find the determinant. We've been doing that before. So if you ever see zeros in any column or any row, you could always expand the determinant about that column and that row. And so because of that, you don't even have to calculate anything. You can always see that the determinant is equal to 0. This is matrix A. It's useful to me because sometimes you spend a lot of time, like if you don't notice that, then you might start expanding the determinant about the first row, and then you wouldn't even realize it until the very end that it all happens to become 0. So kind of keep that in mind. Number 2 is pretty cool. If any two rows or columns are proportional to each other, then the determinant is also equal to 0. Again, this is something that you would look at and say, okay, that's cool. You would never really think about it or know why that's the case. Let me show you real quick. What if you have a very simple 2 by 2 matrix, 1, 2, 2, 4? If I asked you to calculate this determinant, you would do the crisscross method, and that would be very simple. If it were a 3 by 3 or larger, you could use any of the other methods. But the determinant of this matrix is 0, and you can easily see without doing any calculations that it is 0. This second line is a direct multiple of the first line. It's just multiplied by 2. So 1 times 2 is this, and 2 times 2 is this. So this row of the matrix really is just a simple multiple of the row above. Why does that make the determinant 0? Because since I can do row reduction operations to find the determinant, I can simply, if I wanted to, if I were going to do the determinant, I could simply multiply the top row by -2 and add it to the second row. In other words, I would be able to do something like this. I could leave the top row intact. I could say -2 times row 1 plus row 2. That's going to give me a -2, plus here is going to give me a 0. And then if I multiply -2 here, -4 plus this is also 0. This new matrix, from the previous thing we talked about, has zeros across one row, and so the determinant of this matrix here we know is 0. So it's kind of like you can visualize this pretty easily, but you may not always look to see if things are proportional to one another. So if a row in a matrix is simply a scalar multiple of a previous row, then you don't have to do anything. You can just say, it's basically, you might want to show a few steps on the test, but you know that the determinant is 0. Okay? The third one is very, very similar to number 2. If row or column is a linear combination of other rows, columns then the determinant is again equal to 0. And this comes about because of row reduction also. If I had, for instance, a 3 by 3 matrix, and if the third row was a linear combination of the first two rows, in other words, maybe I could just add the first two rows together and get the third row. Or maybe I can multiply the first row times 2 and add it to the second row, which also would give me the third row. Or anything like that. Anytime you can take a linear combination of two rows and arrive at a third row, then because if that's anytime true, I can always do row reduction techniques to make that bottom row 0. Because if it's a linear combination of the other rows, it's almost like being a multiple of those two rows in some combination. I can always then transform that third row into zeros. And so I know the determinant is 0. Now I'm not going to show an example of that, but it's very similar to this one. All right, now I'm going to show you another. These properties are not related to these, but they're very useful. The determinant of the transpose of a matrix is equal to the determinant of the matrix itself. So if you're ever doing a proof or something and you're trying to find the determinant of the transpose, you don't have to do anything. You always know that it's the same as the determinant of the original matrix. Always, always, always. Okay? And then my last one I want to show you before I get to the most important one is the determinant of two matrices multiplied together, A times B, is equal to the determinant of matrix A multiplied by the determinant of matrix B. Okay, this is useful because determinants are hard to calculate with really large matrices. Okay, so if you ever for some reason knew in a proof or a problem that that a large matrix was really the product of two smaller matrices, then you could take these smaller determinants much easier and just multiply them together, and that would give you the determinant of the large matrix. So not terribly common, but occasionally you might use it. All right, now the last property I'm going to show you is actually very, very important. I want you to kind of remember that because as we go on into the next sections, getting into eigenvectors, we're going to use this one. So let me write that down over here on the other board. Remember that we have something called homogeneous system of equations. We haven't talked much about it in this volume, but we have talked about it extensively in volume 1 of linear algebra because homogeneous systems of equations are so darn common, they're everywhere. But they take the general form, some matrix times some column vector with your unknowns, we call it x is equal to 0. Homogeneous means the right-hand side is 0. Turns out that it's very, very common in real systems. Okay, so we're going to study the case of homogeneous systems where A is an n by n matrix. Again, you can have systems where it's not a square matrix, but most of the time you have 3 equations, 3 unknowns, or 4 equations and 4 unknowns, 2 equations, 2 unknowns. So you end up with a square matrix A a lot of times. So we're just going to take a minute to look at this. What is the deal here? Remember, when we studied homogeneous systems of equations, obviously, if the unknown is x, if x were 0, and when I say x, I'm not talking about one variable, I'm talking about all of the variables in the system. So you might have x, y, and z if you had 3 variables, and that's represented by the column vector x, the column matrix x. All right. So anyway, if you had what we call the trivial solution is when this unknown is just 0. Okay, that's always true. Right? But what we're really interested when we solve these things is we really want to look at systems where we have other solutions other than the trivial, the simple, stupid solution when everything's 0. Okay? And we can do a test with using the determinant to figure out when we have other solutions. So the solution is non-trivial, which means it admitting solutions other than x equals 0 if and only if the determinant of the matrix A is equal to 0. This is extremely important, okay? We study these homogeneous systems a lot. We're going to end up studying them a lot in eigenvectors. That's why I'm bringing it up, okay? If the matrix A is square, which means n by n, is usually the case, the solution has non-trivial solution. Trivial means that the solution is silly because, yeah, we know x can be 0. Duh. We want to find solutions when x is not 0, okay? We talked about this a lot before. So this is a test saying if you take the determinant and you get 0 exactly, then this system of equations admits solutions other than x is equal to 0 only in this case. And so, because this is true, I'll just go ahead and state the obvious. If the determinant of A is not 0, then x is equal to 0 is the only solution. And we call that the trivial case, or the trivial solution. So this is basically what you want to remember. It's a test to figure out when these homogeneous systems have interesting solutions, have non-trivial solutions. Because usually in engineering, that's what or science or anything, that's usually what we are interested in. We're not interested in the trivial case. We know that x can be 0. What we want to know is when we have other cases when x can be other than 0. And there are cases out there, depending on what the system is, where this can be solved and you get something else other than x is equal to 0 for a solution. So basically you take the determinant. If you get 0, this thing is what we call non-trivial. It means it admits other solutions. If we get the determinant 1, determinant 2, determinant -10, -45 like we were getting before, then the trivial case when x is 0 is the only solution. We call that a trivial solution. So keep that parked in the back of your mind because when we get into linear independence, when we get to eigenvectors, we're going to come back and revisit that. So kind of keep that. You might want to jot that down. Keep that one in the front of your mind. So make sure you understand these properties. Not all of them you're going to use, but some of them you will, and that's why I'm presenting them here. Follow me on to the next section. We're going to talk about linear independence and vectors and matrices.